Have you ever looked at something you see every day, something tiny, and wondered, how is that actually made? Well, today we're pulling back the curtain on one of the most common objects on the planet. We're about to dive into a secret world of incredible force and fascinating physics.
So, take a look at this. This is a tablet press. And honestly, it's way more than just a machine. It's a high-speed miracle worker. Its one job, to take a bunch of loose, fluffy powder and in a literal fraction of a second, turn it into a perfectly solid, perfectly shaped tablet. But how it pulls that off? Well, that's where things get really interesting.
So what's the secret sauce here? What's going on inside all that shiny steel? How does it manage to apply just the right amount of force to transform total chaos into perfect order? That's the big question, and we're going to answer it by following the journey of a single speck of powder from start to finish.
The entire magic trick, from that fluffy powder to a solid little tablet, it all comes down to one single powerful process: compaction. But what in the world is compaction? Well, let's break it down. It's really made of two key ideas.
Okay, first up, you have compression. This one's super easy to picture. Just imagine you're squeezing a handful of flour. The first thing that happens is all the air between the little particles gets pushed out. The powder takes up way less space. Simple enough, right?
But then comes consolidation. Now this is where the real magic happens. Once all that air is gone, the particles themselves are forced to get up close and personal. They start to interact, to form bonds. This is what gives the final tablet its strength. It's the step that stops it from just turning back into a pile of dust.
And there you have it. You put those two things together, the big squeeze to get rid of the air, and then forcing the particles to lock together, and what do you get? Compaction. It's not just about squishing something, it's about creating a whole new, solid structure from the ground up.
So this whole dance happens in 5 distinct stages. First, the particles rearrange themselves, then they get deformed, and some even fragment. After that comes the all-important bonding, and finally, the great escape, ejection. That's our roadmap. Let's dive into step 1. It all kicks off with a pretty gentle squeeze. You gotta tame the powder, get it organized, before you bring in the heavy machinery.
So the very first thing that happens is just a little bit of shuffling. Think about a jar full of rocks and sand. If you tap it on the table, what happens? The little sand grains wiggle their way down into all the empty spaces between the bigger rocks. That's exactly what's happening here. Under just a little bit of pressure, the smaller particles find all the gaps and fill them in, making the whole mix a lot denser.
Okay, the polite shuffling is over. Now the pressure ramps up, like a lot. We are moving past gentle persuasion and into a world of brute force that is literally going to reshape reality for these little particles.
At this point, everything is packed in so tight there is absolutely nowhere left to move. So as the pressure skyrockets, the particles have no choice but to deform. They're literally getting squashed, changing their physical shape where they touch each other.
Now this squishing or deformation, it comes in 2 flavors. First, there's elastic deformation. Think of a stress ball. You squeeze it, it changes shape, but the second you let go, it pops right back to how it was. Then you have plastic deformation. This is more like a piece of modeling clay. Once you squish it, it stays squished. And for a good, strong tablet, you need that permanent plastic change. For some types of powders, when the pressure gets even more insane, they don't just bend, they actually shatter. This is called fragmentation. And it might sound, destructive, but it's actually incredibly useful. Why? Because all that breaking creates brand new, super clean surfaces, which are just perfect for forming strong bonds in the next step.
All right, we have rearranged, we have deformed, and we have fragmented. We've arrived at the climax of our journey. This is the moment of truth, the instant where loose powder becomes one single solid object.
So how in the world do they stick together? Well, a couple of theories are out there. One is the mechanical theory. It suggests that all these jagged, weirdly shaped particles get forced together so hard they just interlock, like tiny little puzzle pieces. Another idea is the liquid surface film theory, which says that microscopic bits of moisture on the particles act like a glue, helping fuse them together under all that pressure. Whatever it is, this bonding is what makes a tablet that's strong enough to survive. The tablet is formed, it's solid, awesome. But the journey is not quite over.
You'd think we're done, right? Nope.
Now comes one of the most delicate parts of the whole process, getting it out of the mold without it breaking.
We've been talking about these incredible, immense forces, but it makes you wonder, right? This isn't just random smashing. It's a highly, highly controlled process. So how do scientists and engineers actually manage and measure these forces with such pinpoint precision? Well, the answer is this amazing tool called a compaction profile. Think of this graph as the mission control log for making a tablet. It tracks everything. It tracks the pressure pushing down from the top, that's the axial pressure, and it tracks the pressure pushing out against the sides of the mold, the radial pressure. This detailed map lets engineers watch the entire push and release cycle in real time.
So why is this graph such a big deal? Because it's basically a crystal ball. By looking at this profile, an engineer can predict if a particular powder mix is likely to crack. It helps them pick the absolute perfect lubricant for a smooth release. And, most importantly, it makes sure that the final push to eject the tablet is just right, so it pops out perfectly every single time.
So when you really think about it, what's happening here is a perfectly orchestrated storm of physics. You've got rearrangement, deformation, fragmentation, and bonding, all happening under massive forces that are being measured and controlled with mind-boggling precision. And the whole thing is over in the blink of an eye.
It's just like researcher G.S. Patil said. Understanding the physics behind all this isn't just some boring academic exercise. It's absolutely crucial for making the millions and millions of tablets that people rely on every single day.
So, the next time you hold a simple pill in your hand, are you going to see it as just a pill, or are you going to see it for what it really is, a tiny, perfect marvel of microengineering?